Good morning everyone, myself Avadh. I am here to present my research work that is published in SAC 21 as a poster paper. So the title of my paper is again bargaining game based energy aware load balancing in cloud data centers, and this is the joint work which is carried out with Professor Rajdeep Niyogi. He is my PhD supervisor. And in this work, we have considered a very important, or we can say very classical problem, that is called load balancing problem. In load balancing problem, our aim is to basically assign the loads of users to different servers or machines. Here we have considered data centers, so that some quality of service, or we can say some objectives of the users as well as resource provider must be satisfied. Basically, in this work, we have considered the two goals. Basically, first is to avoid the situation of overloading and underloading. That means we have to distribute load to the servers or machines in such a fashion that no server is getting overloaded or underloaded. And second one, that is very important goal, that is to minimize the energy consumption of each data centers. DC here is abbreviation of data centers. So basically this is the architectural framework that has been considered in this work. Here m number of users are here, and we have considered an n number of data centers, where each data center is consist of C1 or different we can say processors, and these processors have similar capacity. And this is the intermediate layer which is consist of front end dispatcher. Here these dispatcher act as a service broker. Basically these dispatchers collect the job of users, and their duty is to map the users job to different data centers. So this is the complete architecture that has been considered in this paper. Next, we have formulated this problem as an optimization problem. So here we have considered that each user has a lambda amount of job to allocate or to execute on different machines. And here, as we have we can see that the load is distributed to different data centers. So we have considered each data center I, or you can as a MM1 queuing system, where the load arrival rate on each queue is phi 1, phi 2 and phi n, because n different data centers are there. So using the concept of queuing theory, we have derived this. The average response time of each DC j, we can say j, is Cj upon mu j plus 1 minus mu j minus phi j. And the energy consumption, basically the energy consumption depend on the utilization of the resources on which this computation is being performed. So the energy consumption, this is a standard formula, that is the energy consumption by a server j is calculated at phi j upon mu j. Basically this is phi j upon mu j is the utilization of server j due to the amount of job that is phi j assigned to the server j, and ej max is the maximum energy consumed when the server is running, this machine is running at its fullest basically. And ej idle is the energy, that is the when this is called minimum energy or idle energy. That means when server or this machine is in idle condition, and this is for one server. And in one DC we have considered there are Cj number of basically servers. So for whole DC the energy consumption is represented using question number 2, that is represented here. So according to these equations, the goal of the load balancing problem that we have considered in this work is to minimize the average response time. That is the aim of a user, that a user want to minimize its response time, as well as the data centers, the resource provider want to minimize the energy consumption. So we have modeled it as a convex optimization problem, where our goal is to minimize this response time of each data center subject to these 4 constraints. So first constraint means there is a each data centers can bear a maximum amount of energy consumption, that is a naught. And this is constant that tells us that energy consumption of a data center while assigning the amount of job, that is phi j, will not be exceed this limit, that is E j naught. And this is the simple conservative constant, and this is phi j must be greater than or equal to 0, and this is the satisfiability constant or stability constant. We can say phi j means the processing speed of a data center must be greater than the job arrival rate. Next, as we have suggested that in this work we have modeled this problem as a bargaining game. So we model this whole scenario as a game. In this game we have considered the cloud providers, or we can say there are n data centers, so we assume that these all n data centers are owned by n different providers, cloud providers. So each cloud provider act as a player in this game, and the job allocation rate phi j that cloud provider j is allowing for his own dcj is termed as the strategy of the phi j. Means what is the strategy of the player? Means player want to only, here player is a cloud provider, so he want to execute only phi j amount of job, and his preference, or we can say his payoff function, is decided on basis of this response time. So everyone want to maximize this payoff, that is why I have used in minus dj phi j. As we have mentioned, there is another goal that they want to consume or waste a certain amount of energy for processing load on their own servers. So we have computed the maximum allowable amount of energy consumption. So this is E j naught, and E j naught is computed using the formula that is mentioned in equation number 2 under this section. So after computing E j naught, we will compute the this is the agreement, basically the initial payoff of the cloud provider without making any agreement. So this is the initial payoff. On this basis they can bargain with each other, so they can come to a agreement point where that if their payoff is less than this initial payoff, so they will break the agreement. So their the payoff that they are going to obtain in the game must be greater than or equal to this U j naught. So basically to solve, basically we have modeled this problem as a game. So this is a cooperative game. So the solution of this type of game is called Nash bargaining solution. So the Nash bargaining NBS of the game is computed by solving the following optimization problem that is defined here. That is j equal to 1 to n ln of mu j naught minus this dj phi j, subject to these three constraints. So this actually the proof of this solution is constructive. We can solve this problem using simple KKT conditions. So while solving this problem, the proof is constructive. So from that constructive proof, we can derive this algorithm. In this algorithm, we can sort each DC according to these values, and after sorting them, we can assign the load of each DCs according to this formula, that is phi j equal to mu j upon 1 minus 2 delta j minus square root of mu j upon delta j, sum of from j to L mu j 1 minus 2 1 minus 1 upon 2 delta j minus sigma sum. Sigma sum is the total amount of job that is arriving on the system, and in this way we can compute the amount of job that is assigned to a particular DC. So that is the algorithm that we have proposed, and in order to evaluate the performance of this algorithm, we have considered two different performance matrices, that is average time and energy efficiency. Average time is defined using this. Energy efficiency basically is the average cost divided by average time. So in this experiment, we have considered this open source available this is data set that is available in open source. So we have considered 1 2 3 4 5 6 12 different client locations, and actually they are the users We have considered their users are situated in these locations and their relative job processing rate is given here, and we have considered some different data centers that I have not shown their configuration in this poster. And in order to present the result of our algorithm, or we have to show the comparative study of our approach, we have compared it with another state of the art non-cooperative game based approach. So the result presented here are basically normalized values. So in order to normalize the results, we have obtained the result for obtained the results of each approach, and the normalization of performance metric values done by dividing the matrix maximum values across all the approaches. So here we have considered two cases: demand versus average time. We have varied the demand, size of demand, that is 50% demand. 50% demand means that suppose the processing capacity of a server or the complete system is 100, so we are just allocating 50 the 50 size of job. So here 60% of the total processing capacity, 70%, 80% and 90%. So we can see here that normalized average time of our approach is in each type of we can say demand is lower than this non-cooperative game based approach. Similarly here we can say normalized energy efficiency of our approach is always less than this non-cooperative game based approach. So this is sufficient to show that the effectiveness of our approach while considering these two performance matrices. And finally, in order to conclude this paper considered an energy aware load balancing problem in cloud computing systems, and the problem we have formulated this problem as a constraint optimization problem. Then thereafter we model this problem into game theoretic setting and computed the Nash bargaining solution of the proposed game. And to assess the relative efficacy, we compared it with an existing approach, and the results confirm the superior performance of the proposed approach. And in last, I would like to thanks anonymous reviewers, referees, and these session chairs. And last, the second author was in part supported by a research grant from Google. Thank you very much. And if you have any question, then please you can mail me, or you can send me in my email ID, that is avadhkishore133@gmail.com. Thank you.